This video will move into section 4.5. The book calls this the substitution rule, but most books that I've seen and most people refer to this as U substitutions. This section, this will be the one higher level antiderivative technique that we will discuss. So just before I jump into the idea and how we use it, I just want to take one moment to go back and point out, because we will use this technique for both definite and indefinite integrals. So I just want to remind us, just again, the big picture, that if it's a definite integral, that we're specifically referring, this tells us to find the area under this function from x equals a to x equals b. And by the way, this is also going to bring up the importance of the dx notation, that in this setup, that the dx, when we wrote this initial definition of a definite integral, we had the limit as n goes to infinity of the summation of fx sub I times delta x. Essentially, the delta x became the dx, and we just dropped the subscript, and that summation became an s. But again, I'm just trying to point out that dx was there for a reason, that these values were x values. So finding the area under this function from this x to this x. Over here, the indefinite integral, well, this was telling us to find the general antiderivative. But just like derivatives, we need to know with which variable we are finding the antiderivative with respect to. And that's, again, what the dx is doing here. So it kind of seems like the dx wasn't super important, but now as we learn this new technique, we'll see that that dx is essential. That if you kind of forgot it in some of the earlier problems, it doesn't really lead to an issue, but it will lead to an issue with some of the harder problems. Because why does this technique go with both of these? Well, big picture, both of these, you're taking an antiderivative. Right? This one, you take the antiderivative plus c and you're done. This one, you take the antiderivative. You still have to mark the bar, and then you finish this up by plugging in the b minus plugging in the a. But both of these, the definite and the indefinite integrals, our typical solution involves getting an antiderivative. I say typical. The book snuck in one or two problems back when we first introduced this, that even knowing the fundamental theorem, we still can't solve by traditional techniques. Okay, so now, how do we get into U substitutions? What is the antiderivative technique? How does this work? And just before I show you this, I just want to make this one little note. As we do this, in this class, it feels like we have such concrete rules for antiderivatives. And for the most part, we do. But as you move on, and as some of you move into Calc 2, you'll start to realize more and more that it's really just general ideas. And how do you know your antiderivative is correct? It's correct if it works. That's almost a terrible thing to say, but really the idea of an antiderivative is if you take the derivative and go back to where you were. So we make it seem like we have these concrete rules, and we do have concrete rules for regular derivatives, but for antiderivatives, this is more just a general idea. We do what needs to be done. But so far, everything that we've seen, either we already had nice addition, subtraction, or we could multiply or divide if we had extra problems there, or we had some basic rewrites, or if we had trig functions, there were ways we could manipulate to have known antiderivatives. But now, what if we get to a problem where we can't do that stuff? So I'm going to already just jump in. Let's evaluate, and let's start off with the integral. I'll make this one an indefinite, but in a few moments you'll realize definite is going to make a very, very minor difference. So we'll start indefinite. The integral x squared times the quantity x cubed plus 1 to the 5th power dx. If I want to solve that antiderivative, well, by our traditional techniques, we would say this one is a little bit of a mess. We would realize that I've got multiplication here and I've got some inner outer. Now, With our traditional techniques, we could actually make this one work, but we'd have to multiply everything out. So I'd have to start by FOILing this out 5 times and then distribute an x squared. So while this one, we could handle this with our regular techniques, but it's impractical. And then this next one, if I change that to the square root of x cubed plus 1, now there is no multiplying this one out. Now I've got multiplication that I'm stuck with. And similarly, in this one, so all 3 of these are similar. This one we could fight our way through with traditional techniques, but both of these we'd be completely stuck. Multiplication, multiplication, and multiplication that we can't clean up. There is no product rule for antiderivatives, and there never will be. So this is the situation that we will apply this new technique that we're calling a U substitution. So I'm trying to set the stage for some problems, and these are not the easiest ones, but they definitely demonstrate situations that a U substitution will work. I want to take a quick moment to point out what the book says about this. And I don't think there's anything, there's nothing wrong with what the book says. I just think there's a few ways we could interpret what they do a little bit easier, a little bit better. So the book says if we are trying to find, again, definite or indefinite, that doesn't matter, but if we have this type of setup, if we have this type of setup with our integral, then we will make a U substitution of U equal to gx. I hate that description, everyone. It initially has at least one right component, but the book, I feel like it harps too much on you looking at this interior function, seeing an inner-outer setup, and seeing the derivative of the inner somewhere inside of this. That is really, really taking a big jump. So while that is basically correct, that is an idea that we are going to basically mimic, but I hate all this extra notation. And I think for most people, all we're looking at is if we're in a situation we can't take the antiderivative by traditional techniques, well then we're using our U substitution as a last resort. So again, if we see multiplication, division, or even just some inner-outer mix that we're a little unprepared for, we'll make a U substitution. And for me, I typically talk about starting off. As some of you go into Calc 2, U substitutions, we'll learn some more tricks on how to use them. But even there, we often talk about looking at U as something that's trapped inside. And then as soon as we identify U, then we will move right into du, which is a little bit short for the derivative of function U. And this is where there's some sense of implicit derivatives come up here. But again, we'll see a few ways to make this work. And I'll point out just the tiny, minute differences from what I do compared to what the book does. So basically, if we're in trouble, and you have to start that way, everybody, if you get rid of this exponent of 5, there's no reason to even think about a U substitution. We'd say, oh, that's just multiplication, multiply it out, x to the 5th plus x squared, and you would have a simple antiderivative. That's it. So it's only if we're in trouble. And if we're in trouble, then we will start to consider let U be the inner piece, and then we will take the derivative of U. From that point, we will then substitute, and I'll show you how that works. And then after we substitute, this should simplify the integral in some way. So once that integral is simplified in some way, then we can take our antiderivative, but then we often have this step of back substituting. So this is a very generic list, but it kind of gives us a nice track. First things first, identifying a situation that we need a U substitution, and then moving into identifying u and finding its derivative. Step 2 is this sense of substituting. Step 3 is simplifying. Step 4, taking the antiderivative. Step 5, back sub if necessary. So now let me apply that up here. So for this first problem, we recognized we need a u sub because we're in some trouble. So I pick u as what's inside. Inside, outside. This really goes back, if you're thinking about derivatives, with the idea of chain rule. If you were taking a derivative here, you'd have product rule, but this part of the product rule would require chain. I don't like you to think of it that way, but I'm just trying to get you to I'm trying to point you to the things you should be looking for. So I see a big mess here, but this is the inner outer, so I pick u just as the inner. So now du, this is where the notation kicks in, but this is really notation for the derivative of u. So if u is this, well then what is the derivative of u? Take a derivative using your traditional derivative techniques. And by the way, that's something that feels weird for a lot of people, where big picture, we're trying to take the antiderivative of this, but in the middle of the problem, we're taking a regular derivative. So just be careful with that. A regular derivative, this would be a 3x squared, but technically there's aspects of implicit derivatives here, that this is either du over dx, but what will make our lives even easier, just mark everything. Technically, you took a derivative of u, you got 1, and it gets marked du. And then over here, you're taking a derivative, you get 3x squared, and I will mark that dx. That's the first big difference from the book versus what I do. The book does du over dx equals 3x squared, but then even though that's derivative notation, it treats it like a fraction and multiplies the dx over. Now here's the second difference between my little idea and what the book does. The book would then take this, would recognize, hey, you've got an x squared and a dx, but you're missing the 3. So it moves the x squared next to the dx. It just changes the order. It puts this in front and the x squared comes after. But then it notices you need a 3x squared. So how do you get a 3 in the middle? Well, you multiply by 3 and at the same time you multiply by 1/3. And now you get a clean substitution. But I think that's awful, everybody. I think what is easier, and in my experience, what makes this a much more repeatable process for students to follow, is to always solve this for dx. That's why this was so important in the notation, everybody. When we start getting to this line that I call substitute, it's not just substituting in the main function, it's also getting rid of this as well. Big picture, what we are trying to do through this technique is to essentially change the problem. By changing the variable, that we could somehow simplify the problem so that we can take our antiderivative using traditional techniques. So the way to make the simplifying easier, the substituting and the simplifying easier, in my opinion, is to always solve this for dx. So I'll divide the 3x squared over to the other side, and now I'm substituting. So now I'll come back to my integral. I still have not taken the antiderivative. Don't lose your integral notation. I still have not taken, let me mark this. This is problem number 1, so I'm continuing. And this will be number 2, and this will be number 3. So working on number 1, there's my u sub. For the moment, the x squared is just hanging out. But right here, this is what we defined as u. So this will now be u to the 5th power. Remember, we just picked u as what was the inner piece. That exponent of 5 is still there. So I get u to the 5th power. But now the dx. The dx we've now isolated is du over 3x squared. So all of this is being substituted in place of this. So I will get du over 3x squared. If we did all of this correctly, we know, and again, this really goes back to first things first, did we even need a u sub? So if we needed a u sub, we picked the right u, we found the right derivative. I mean, if we made a goof, if we accidentally got the derivative was 3x, we forgot the exponent, or accidentally did an antiderivative and got x to the 4 over 4, this next simplified part wouldn't work well. So if we've made the right decision to make a u sub, found the right u, found the right derivative, substituted correctly, the integral should naturally simplify. And that's what we should be noticing here. The x squareds would cancel. So simplifying the integral really means that you're converting to your new variable. So now I should have no more x's or thetas or t's, whatever our original variable is, and we should have completely transformed this into a new integral in terms of my new variable u. And that's exactly what we have here. The x's are gone, that 3 is in the denominator, so that's a 1/3. Rules of integrals, antiderivatives, kick it out in front of the integral, keep it in front here. That doesn't make a difference. I still have my integral. I still have the u to the 5th du. This is where we started. We established this u substitution, and this is the new integral we came up with. If we did everything correctly, again, no more x's, but we should also be simplified enough, maybe not directly, but within, a minor rewrite or something like that, we should be ready to take the anti. And look what happened. We started with a mess of multiplication and inner-outer. By making the right choice with u, now everything is simple. All I've got, there's no fancy multiplication anymore. Number out in front just kicks along. The anti of u to the 5th is 1/6 u to the 6th. I still found an antiderivative, so something comes at the end. This was an indefinite, so that will be a plus c. Now, just little things, good habits, right? 1/3 times 1/6 is 1/18. But this is the real big last step, everybody. Evaluate this integral. Find this general antiderivative. Well, the one big thing missing, while this is a correct anti, the one issue is that we started in terms of x, we switched the variable to u to make the antiderivative work. Remember, the u substitution was working here, but we didn't just back sub, we still actually needed to take the antiderivative. But now my antiderivative is in terms of u, but the original problem was in terms of x. That's where we have to back sub to finish this problem. And all I do to back sub, in place of u to the 6th, what was u? So this became 1/18 x cubed plus 1 to the 6th power plus c. That is my final answer. We still found an antiderivative, so I could still test my work by taking the derivative. And you'll notice, pretty much, it's not 100%, but pretty much every problem that you needed a u substitution for the anti, you would need chain rule for the derivative. The whole idea of this idea for a u sub is based off the fact that you used chain rule in some form to get this. So looking at chain rule, 6 times 1/18 is 1/3, x cubed plus 1 to the 5th times an extra 3x squared. The 3 and the 1/3 cancel, and there is your x squared, x cubed plus 1 to the 5th. So just because we learned a little bit of a fancier technique, nothing's changed. It still is an antiderivative when we're done, so we can still test our answer by taking the derivative and checking that everything is correct. Now, before I keep going here, I have several things I want to point out. Number one is that, again, these are antiderivatives. And for some students, some people notice things a little bit easier than others. So some students can kind of look at this and realize this is the main piece. And that, okay, I would have had to add 1 to the exponent and divide by that. And there are some students who never really make a U sub, but they just keep playing games. They can kind of methodically work their way to here and keep playing games with this until the derivative of this matches this. I could say I did that for a little while myself, but I have to be honest, that's a bad habit to get into right now. Because even if you understand that, if you're going into Calc 2, some of these problems will just get a little bit too tough for that. So you need to have some concrete way of putting together a U sub. So like I said, this is a good way to start. Calc 2, you'll get some other options. Even after I finish these problems, I'm going to go back and make a whole chart, and we'll point out a U sub, well, U as the inner piece is the main idea, especially at this stage in the class and even the beginning of Calc 2. But eventually, it's more about making U to match something on your chart. So we'll even see a tiny bit of that here. But now, let's go to page 2. I want to do these problems that I mentioned before, but I also want to go back and take another look at the problem we just did. I set you up initially with x squared times x cubed plus 1 to the 5th dx and had this as a indefinite integral. Now let's see what happens if this is a definite integral. So let's go from 0 to 2. Honestly, almost everything is exactly the same, because even a definite integral, we still need the antiderivative. So I'm still in the same stuck position here that I was here, that I have multiplication and inner outer. And that inner outer is making this a pain that I can't just distribute that and get rid of the multiplication and make this a simple function. So I would do the exact same thing. I let u be the x cubed plus 1, du would be the 3x squared dx. I'd make the whole substitution. But this is what I want to jump to, everybody. Again, what we are formally doing here is transforming this as an integral in terms of x into an integral in terms of u. And if we do it correctly, things should simplify so that in terms of u, we should have an easy function that we can finish. But when you have a definite integral, these bounds are also in terms of x. So, two things. As you're making the substitution, I'm doing this a little quickly because it's following the exact same thing we did here. So I've got a 1/3 u to the 5th du. First thing, do not include the 0 and 2 on this new integral. These were bounds in terms of x. You've now turned this into u. So two options. Either you don't put the bounds here. You put the bounds here, you get in trouble, everybody, because the next line, you go 1/18 u to the 6. This is a definite integral, so you get the bar, and people put the 0 and the 2 here. But the 0 and the 2 go with x, not with u. So two options, everyone. Either you don't put the bounds in, you take the antiderivative, but you don't put the plus c, because you remember it really is a definite integral, so you put the bar, but now you back sub, like we did on the previous one, but now you still have the bar, and now you go back to those same two original x's. That's the big deal, everybody. You still, in this form, have to back sub, and you would do that back substitution before you plug your x values in. And now we'd be back on track. So I would get that this equals 1/18. When I plug in the 2, 2 cubed is 8. 8 plus 1 is 9. So 9 to the 6th power minus 1/18. I plug in 0. I get 1 to the 6th power. So this is 1. And, do a little more arithmetic. But that would be a good final answer. So you still did a u substitution. You just ignored the bounds until you got to the end of the problem. You still did the bar because you knew the bounds were here, but as you back subbed, that's when you got the original bounds, and then that's when you plugged in. The alternative Some people hate this alternative because they really need to get used to the idea of back substituting. That if you have an indefinite integral, there's no choice. You're not done here. You have to back sub and get it back to the original variable. And that is when you were done. But if you're in a definite integral, this is where the alternative comes up. As soon as you realize you have the right u substitution and that you're able to plug in the original variable canceled, what you can do is referred to as pushing the limits. That these limits are in terms of x. Well, take those as x values, use the equation that converts x's into u's, and get new values. So if u is 0, 0 cubed plus 1 is 1. My new u value that corresponds with x is 0 is u is 1. And then do the same thing for the top. When x is 2, 2 cubed is 8, 8 plus 1 is 9, so when x is 2, u equals 9. I've completely transformed the integral. Not only just the function itself, I've also pushed the bounds in terms of my new variable. So now with this setup, now I can take my antiderivative, and now I can do these new bounds in terms of u, and look what happens. I plug in the 9 first, and I get this, minus I plug in the 1 second, and I get this. So this matches exactly what we had here. As you go into Calc 2, I often talk about, I think pushing the limits is a worthwhile thing to get used to. But in Calc 1, like I said, we're literally just learning this technique. So a lot of people always like to back sub. Get it in terms of u, get your antiderivative. And if it was a general antiderivative, if it was an indefinite integral, back sub and you're done. If it was a definite integral, back sub, get the original bounds in, and then plug in and you're done. Okay, so now let's move into problem number 2. And realize this is really the same situation as this. At the very beginning, we pointed out we could theoretically multiply all this out, but it was just too much work. If this was x cubed plus 1 squared, foiling it out once, distributing an x squared, that's not terrible. But to FOIL this out 5 times, again, that's just not practical. But down here, there is no option. But we're really in the same situation we were here. Multiplication, inner, outer, I'd still pick the exact same u. I'd still take the derivative. I'd get the same du. I'd solve this for dx. I'd substitute that in. Just one little thing, the square root of u, I'm still going to have to rewrite that as an exponent. I could leave it as the square root of u, but in a moment I'm going to have to do that anyway. The dx is now du over 3x squared. The x squared still cancel. It's not just enough that x, like if this was an x to the first and that was an x squared, it's not just enough that they simplify. The previous variable has to cancel entirely. Okay. This has now become, I like to kick these numbers out in front, but like this is the exact same thing as this, so it doesn't matter which way you look at it, but we need to realize here, just like we saw here, everything is working. All the x's canceled, and now if I hadn't already switched that square root into a fractional exponent, now would be the point that I have to. I've simplified the problem, and I'm still using a power rule to finish. 1/3 pushes along, new exponent is 3/2, so I'll get a 1 over 3/2, a 2/3 out in front. This was an indefinite integral plus 3 plus c. And again, I could clean this up a little bit, but the biggest thing that is a must is to get this back to x. So right here, I'll make that a 2/9. And do you rewrite this as the square root cubed? That's irrelevant, but get the x back in. X cubed plus 1 to the 3/2 plus c. And very similar with number 3, the integral x squared cosine x cubed plus 1 dx. One more time. Same situation. Problem with multiplication and some issue with inner outer. And one more time, the inner is that x cubed plus 1. So the du the exact same way. I'm already just going to simplify, solve for dx. As I substitute x squared, now I'll get cosine of u. Parentheses or not, that doesn't matter. It's simple enough. Here I needed the parentheses to make it clear the plus 1 was also a part of the angle inside the cosine function. But now that u is clearly a part, the dx, du over 3x squared, x squareds cancel. One more time, the 1/3 left behind. But now, that's finally the biggest difference. These two are almost identical because after we got rid of my u to clean things up, I was simply left with u to a power, u to a power. But now I'm left with a trig function, but this is a good antiderivative. How do you take a derivative and get to cosine? You started with sine. The 1/3 pushes along. The derivative of sine is cosine. And there's no extra plus or minus here, right? Sine has a direct derivative of cosine, but it's still to backs up. 1/3 sine x cubed plus 1 plus c. Okay, so this was a good start, but now I'm going to do a second video as we do more problems and just, again, overall get a little more practice with u substitution. When we finish this semester, I have a little packet that I like to give out for my students when we're beginning a Calc 2 class. I will share that with you, and I will tell you that for a lot of my students who struggle in Calc 2, u substitutions is a very, very common frustration. It often gets done quickly at the end of Calc 1, so some students don't realize how significant and important it is as they go into Calc 2. So for us, I don't want to kill us with u substitutions. We do have a last quiz. There'll probably be 1 or 2 u substitutions necessary on that quiz. On the final, same thing, maybe 1 or 2. So we'll see it a little bit here, but I have to stress this is a very important technique and gets used a lot in Calc 2.